In the mid-20th century, the prevailing scientific model for Venus described a wet, tropical planet. Because the cloud cover was so dense, astronomers assumed the surface was shielded from the sun, creating a humid swamp potentially capable of supporting life. This assumption was so embedded in the mission planning that early Soviet probes included sensors specifically calibrated to detect water. The reality was the exact opposite. The atmosphere was not a shield. It was a lid that trapped heat, creating a runaway greenhouse effect with surface temperatures of about 475 degrees Celsius. The first few probes didn't just fail, they were physically obliterated by the immense atmospheric pressure before they could transmit a single image from the surface. This failure created a new consensus. Even if a lander survived, photography was useless. The atmosphere was 90 times denser than Earth's. Scientists predicted that little to no sunlight could penetrate that depth, meaning the surface of Venus was locked in perpetual absolute darkness. The Soviet engineers ignored this model. They equipped the Venera 9 lander with a floodlight, just in case, but they also programmed the camera to scan immediately upon landing. The footage that returned proved the darkness theory wrong. But it was the later missions, specifically the panoramas from Venera 13, that sent back data no one can fully explain even today. The Soviet engineers were working with bad data. In 1967, the accepted model suggested the surface pressure of Venus was roughly 20 times that of Earth. This was high, but manageable, with reinforced aluminum. The Venera 4 probe was built to these specifications. It entered the atmosphere and deployed its parachute, expecting a slow drift down to the surface. It never made it. The probe stopped transmitting at an altitude of about 27 kilometers. It did not burn up. It was physically crushed by the pressure, which far exceeded its structural limits. The atmosphere at that altitude was already surpassing the probe's designed capacity, and it was nowhere near the ground. This failure revealed the scale of the problem. The pressure wasn't 20 times that of Earth. It was closer to 90. At the surface, that is the equivalent of being 1 kilometer underwater on Earth. The team had a limited window before the next launch opportunity in 1969. They could not redesign the entire pressure vessel in time, so they tried to bypass the problem through descent speed. For Venera 5 and Venera 6, they reduced the size of the parachutes. The logic was simple. If the probe fell faster, it would spend less time in the upper atmosphere. Hopefully, it would reach the surface before the heat and pressure destroyed it. The plan failed. Both probes imploded roughly 11 kilometers above the surface. This forced a total redesign for Venera 7. The engineers abandoned the idea of a standard aerospace vehicle. They effectively began building a submarine. The new design featured a forged titanium sphere capable of withstanding 180 atmospheres, double the expected load. They removed almost all scientific instruments to save weight for the armor. The windows were removed. The solar panels were replaced with a heavy internal battery. Venera 7 launched in August 1970. Upon arrival, the parachute reefing cords melted, causing the parachute to fail during the final stage of descent. The probe didn't float down. It fell. It impacted the surface at roughly 17 meters per second. In mission control, the telemetry stream flatlined immediately. The mission was marked as another failure. It was only during a post-mission review of the raw radio tapes that an astronomer noticed a pattern in the static. The probe had not died. It had toppled over on its side, pointing its antenna away from Earth, but it was still whispering. By processing the noise, they recovered 23 minutes of temperature data from the surface. It was the first time a human machine had transmitted data from the surface of another planet. The data confirmed the surface was roughly 475 degrees Celsius. It proved a machine could survive, but it also proved that any camera sent to this world would need to be built like a tank. The survival of Venera 7 proved that a titanium sphere could resist the crushing pressure of 90 atmospheres. The problem for the next generation of probes was the temperature. The surface of Venus sits at 475 degrees Celsius. This is hot enough to melt lead, zinc, and tin. It is also hot enough to destroy standard silicon electronics instantly. The engineers could not simply insulate the lander. Insulation only slows down heat transfer. Eventually, the heat gets in. They also could not use active cooling systems like fans or radiators. A radiator works by dumping heat into cooler air. On Venus, the air outside is hundreds of degrees hotter than the machinery inside. The solution was to turn the lander into a temporary heat sink. Before the lander separated from the orbiter, the system circulated super-cooled fluid through the pressure vessel. This brought the internal temperature of the probe down to -10 degrees Celsius. This gave the probe a thermal head start. It essentially began its mission as a block of ice falling into a furnace. To handle the heat generated during the descent, the engineers used a phase change material. They packed the interior with lithium nitrate trihydrate. This chemical has a melting point of 30 degrees Celsius. When a substance melts, it absorbs a massive amount of energy without rising in temperature. As the heat from the Venusian atmosphere penetrated the titanium shell, it went into melting the lithium nitrate, rather than frying the electronics. This bought the lander roughly 50 to 60 minutes of operational time before the system boiled over and failed. The camera itself required a completely different approach from standard photography. A television camera from the 1970s used a cathode ray tube. These tubes were large, fragile, and required glass lenses that would crack under the external pressure. The engineers could not risk putting a large glass window in the side of the pressure vessel. A structural failure there would cause an immediate implosion. Instead of a camera, they built a telephotometer. This is a mechanical scanner rather than a lens-based imaging system. The device remained safely inside the cooled titanium sphere. It looked out through a tiny cylindrical quartz window that was thick enough to withstand the pressure. The mechanism was simple and robust. A small mirror rotated back and forth behind the window. It collected light from a single point on the surface and directed it into a sensor. The sensor measured the brightness of that single dot. Then the mirror moved slightly to measure the next dot. The probe transmitted this data as a stream of numbers. It did not send a video signal. It sent a long string of telemetry that Earthbound computers reconstructed line by line. This method was slow. It took many minutes to build a complete panoramic image. If the probe overheated before the scan was finished, the image would cut off. The engineers were trading speed for durability. They were betting that a slow, mechanical eye had a better chance of surviving the conditions than a complex electronic one. On October 22, 1975, Venera 9 survived the descent and transmitted data for approximately 50 minutes. It landed on a steep slope of roughly 20 degrees. The engineers had prepared for the worst-case scenario regarding visibility. They assumed the thick clouds would block all sunlight, plunging the surface into a deep twilight or total darkness. To counter this, the lander carried powerful halogen floodlights to illuminate the ground in front of the camera. When the lens cover popped off, the sensors detected immediate illumination. The floodlights were unnecessary. The surface of Venus was not dark. The ambient light levels were comparable to a cloudy summer day in Moscow. The thick atmosphere scattered the sunlight evenly, creating a soft, diffuse glow that eliminated harsh contrasts, but provided plenty of light for the telephotometer. The camera began its scan. It took 30 minutes to build the full panorama. As the data arrived on Earth, the scientists saw something that contradicted years of theory. They expected to see a sandy desert or a landscape worn smooth by erosion. The atmosphere was dense, so they assumed strong winds would scour the rocks down to pebbles. The image from Venera 9 showed the opposite. The ground was covered in sharp, angular rocks. The edges were jagged and broken. This implied that the surface was geologically young. It also proved that the wind speed at the surface was negligible. The rocks had not been eroded by wind or sand. The atmosphere was calm. The image also revealed the clarity of the air. There was no fog or dust near the ground. The horizon was clearly visible in the corners of the panoramic frame. The probe was sitting on a pile of tectonic debris, likely a result of the landing itself or a recent geological shift. 3 days later, Venera 10 landed over 2,000 kilometers away and operated for 65 minutes. It touched down on a much older, smoother plane. Its images showed flat slabs of rock resembling dried magma flows. The difference between the two landing sites proved that Venus was not a uniform wasteland. It had distinct geological regions. It had mountains, slopes, and plains. The primary discovery, however, remained the light. The fact that the sun could penetrate 90 atmospheres of carbon dioxide showed that significant diffused sunlight reached the surface, contradicting earlier predictions of total darkness. These two black and white images were the first direct look at the surface of another planet. But they were limited by their lack of color. The scientists could see the shapes, but they could not see the true nature of the chemical world they had touched. In March 1982, the Soviet Union launched the Venera 13 and Venera 14 missions. These probes represented the apex of the program. They were heavier, smarter, and carried more instruments than their predecessors. The primary goal was no longer just to prove the surface existed. The goal was to characterize it chemically and visually. To do this, the engineers upgraded the telephotometers to capture color. Venera 13 landed on March 1st, 1982, and survived for a record 127 minutes. It began its scanning sequence immediately. The camera did not take a single color photograph. Instead, it took multiple scans using red, green, and blue filters. The data was recombined on Earth to create a composite color image. The result was startling. The black and white images from 1975 had shown a stark, rocky world. The color images revealed a landscape bathed in a suffocating, deep orange glow. There were no other colors. The rocks were orange, the sky was orange, the horizon was orange. This was not a malfunction. It was a result of atmospheric physics. The atmosphere of Venus is so thick that it acts as a massive filter. It absorbs the blue and green wavelengths of sunlight as they pass through the clouds. Only the red and orange wavelengths reach the surface. To verify this, the lander carried a color calibration chart within the camera's field of view. The chart contained strips of white, red, green, and blue paint. In the transmitted image, the white strip appeared orange. The blue strip appeared almost black. This proved that a human standing on Venus would see the world in sepia tone. The brain would not be able to color correct the scene because there is no white light reference. Venera 13 also broke new ground in audio. It carried a Groza 2 microphone. This instrument was designed to detect seismic activity and atmospheric discharges, but it also functioned as a standard audio recorder. It captured the first sounds ever recorded on another planet. The recording revealed two distinct types of noise. The first was the wind. The telemetry indicated a wind speed of roughly 0.5 meters per second. On Earth, this is barely a breeze. On Venus, the air is 60 times denser than Earth's atmosphere. A wind moving at 0.5 meters per second pushes with significant force. The microphone picked up a low, constant aerodynamic drone as the thick air flowed over the lander's structure. The second sound was mechanical. The probe successfully deployed a pneumatic drill to collect a soil sample. The microphone captured the sharp, explosive sound of the pyrotechnic charge firing the drill mechanism. It then recorded the grinding noise of the bit cutting into the basaltic rock. This audio confirmed that the dense atmosphere was an excellent conductor of sound. The environment was not just hot and pressurized, it was noisy. Venera 14 landed 4 days after its twin, on March 5, 1982. It touched down in a lowland region, roughly 1,000 kilometers away from the Venera 13 site. The terrain here was flatter and smoother. It resembled a cracked pavement of basaltic rock. The mission objectives were identical to the previous landing. The probe needed to photograph the surface, analyze the atmosphere, and physically test the ground. One of the key instruments on the lander was a spring-loaded arm. This device was designed to swing out from the base of the probe and strike the ground with a known force. By measuring how far the arm penetrated the soil, scientists could determine the physical density and compressibility of the Venusian surface. It was a simple mechanical test, intended to tell us if the ground was soft dust or hard rock. The landing sequence was automated. First, the probe secured its footing. Second, the cameras began their operation. The lenses were covered by titanium caps during the descent to protect the optics from the heat and pressure. Once on the surface, pyrotechnic charges fired to eject these caps. The caps popped off, clearing the view for the telephotometers. On Venera 14, the lens cap ejected exactly as planned. However, it did not roll away. It landed directly on the spot where the compressibility arm was programmed to strike. A few moments later, the arm deployed. It swung down and hammered the object directly beneath it. The telemetry sent back to Earth indicated that the surface of Venus was incredibly hard and rigid. It showed zero compressibility. This was technically accurate data. The probe was not measuring the soil. It was measuring the titanium lens cap it had brought from Earth. The camera scanned the area and sent back an image confirming the failure. The photograph clearly shows the arm pressing firmly down on the center of the discarded lens cap. The actual surface of Venus lay only centimeters away, untouched. The incident remains the most famous mechanical failure in the history of the program. It highlighted the immense difficulty of remote operations. The engineers had successfully navigated millions of kilometers of space, survived re-entry, and landed in hell, only to be defeated by a piece of their own safety equipment. The mission data sat in the archives for 30 years. The scientific consensus remained that Venus was sterile. The surface temperature and pressure made organic chemistry impossible. In 2012, however, Leonid Ksanfomality published a paper that challenged this view. Ksanfomality was not a fringe theorist. He was a respected contributor to the original Soviet space program. He decided to re-examine the raw panoramic sequences from Venera 13 using modern digital image processing techniques. His analysis focused on the timeline of the images. The telephotometers did not take a single snapshot. They scanned the scene repeatedly over the course of the probe's life. By aligning these sequential scans, Ksanfomality looked for changes between the frames. He found them. He identified several objects that appeared to behave erratically. The most prominent anomaly he named the scorpion. In the early scans, the soil is empty. In a scan taken 7 minutes after landing, a structured object appears. It is approximately 15 centimeters long. It seems to have a central body and a curved tail. In the subsequent scans, the object is gone. Ksanfomality argued that the object emerged from the soil, remained visible for a short period, and then moved out of the frame. He also identified an object he called the black flap. This object appeared to change its shape and position relative to the probe. He famously stated that these objects emerged, fluctuated, and disappeared. He suggested that the inhabitants of Venus might utilize a form of life based on exotic chemistry, rather than carbon and water. The global scientific community rejected his conclusions. NASA scientists and other Russian experts provided a mechanical explanation for the anomalies. They argued that the scorpion and the flap were likely pieces of the lander itself. The probe was wrapped in layers of insulation and plastic. As the internal temperature rose, these materials began to melt, peel, and fall off. The movement was not biological. It was the result of the lander disintegrating under the thermal stress. The shifting shadows were likely caused by the changing angle of the sun or the settling of the lander into the soft soil. Subsequent analyses and improved image restorations have confirmed these features as artifacts, noise, or detached components of the lander rather than evidence of life. Despite the rejection of the biological theory, the analysis revealed something unsettling about the footage. The surface of Venus was not a static painting. It was a dynamic place. Things moved. Debris shifted. The lander groaned and warped. The footage did not show a dead world. It showed a violent interaction between the machine and the environment. The impossible shapes were likely the dying convulsions of the probe itself, captured in slow motion by the scanning camera. The camera on Venera 14 was the last eye humanity opened on the surface of Venus. After 1982, the Soviet priorities shifted. The engineers realized that landing in random spots provided excellent close-up data, but it could not map the entire planet. To understand the geology of Venus on a global scale, they needed to see through the clouds from orbit. Venera 15 and Venera 16 launched in 1983. They did not carry landers, they carried massive synthetic aperture radar systems. These probes mapped the northern hemisphere of the planet. They revealed shield volcanoes, lava channels, and tectonic fractures. The data was scientifically invaluable, but it was abstract. It was a topographic map, not a photograph. The final Soviet missions to Venus, Vega 1 and Vega 2, launched in 1985. These were hybrid missions designed to intercept Halley's Comet. They dropped off landing units at Venus on their way to the comet. These landers focused on soil chemistry and atmospheric analysis. They also deployed balloons that floated in the upper atmosphere to measure wind speeds. They did not carry cameras. The engineers decided that the weight of the imaging system was better spent on other instruments. With the collapse of the Soviet Union, the program ended. The data from the Venera missions was stored on magnetic tapes. Over time, the physical media began to degrade. The images that appeared in newspapers and scientific journals in the 1970s and 80s were often grainy and low contrast. They were analog reconstructions of digital signals. In the 2000s, a new generation of researchers began a process of digital archaeology. They went back to the raw telemetry data. Modern computers could process the signal noise much more effectively than the mainframes of the 1980s. They filled in missing pixels and corrected the geometric distortion caused by the panoramic mirrors. This restoration work revealed details that had been invisible for decades. The new images showed the texture of the soil and the layering of the bedrock with unprecedented clarity. They revealed the horizon line was further away than previously thought. Today, these restored images remain the only direct ground-level optical photographs ever taken of the Venusian surface. Subsequent orbital radar missions and more recent observations, including near-infrared detections by the Parker Solar Probe that sensed faint thermal emission from the surface through atmospheric windows, have added valuable new perspectives. However, no mission since has returned new photographs captured from the surface itself. Every other image of Venus you see is either a radar map, an artistic rendering, or a photo of the cloud tops. We have sent rovers to Mars that stream high-definition video daily. We have flown past Pluto. Yet for the planet closest to Earth, our visual understanding is frozen in 1982. We rely on data collected by a titanium sphere that melted 40 years ago. Until a new lander survives the descent, the yellow rocky plains of the Venera panoramas remain our only true view of hell.